Hello Kidlets, this is your third video in the Starlight and Telescope section. Today we are going to be looking at spectra. Spectra and the light and elements emitted from a star or a galaxy can tell us a lot of different information about a star. We can determine the composition, the radius, the temperature, velocity, mass, and also rotation period. So all of that information is from that incoming light. We can also see if it's passing through a gas or what sort of elements are present in the gas that it's passing through or in the star itself. So this is an example of an absorption spectra, and we can see that lines of hydrogen, sodium, and magnesium have been absorbed, leaving dark lines, and that would give us information about the phase that the star is in, the composition of it, if it's going to supernova or not, and what sort of phase of stellar evolution that star would be in. In the previous slide, in that example spectra I gave you, each of those dark lines is called a spectral line. And spectral lines are specific to a particular element. We could think about spectral lines as being like a fingerprint. Just like you guys all have specific fingerprints, stars do as well. So spectra is like the chemical fingerprint of a particular element. So this is caused by having photons that are either emitted or absorbed as you have electrons that change transition regions. So when a particular wavelength interacts with an atom, if it is the specific type of wavelength needed for that atom, you can have an electron that either moves up or down in energy level, and if it does that, it can kick off a photon. And that then would be the light that we see, and that would emit the spectral lines that are observed. So here we have an atom, we have the nucleus here, we have the electrons surrounding the nucleus, and remember that the number of electrons is determined by the atomic mass. So we have a set number of electrons, but you can have energy that can interact with that atom and cause that electron to temporarily change shells. So each of these atoms has a specific pattern that it can have. But you can have the electrons that jump between shells, and that can either absorb or emit a photon. So the ground state would be the natural state. If that electron is kicked up an orbital level, it's going to absorb a photon, and that would give us an absorption spectra. If it is knocked down a level, it is going to kick off a photon and give us an emission spectra, and that would be where we'd emit a photon. So when it is elevated, we call that the excited state. In its natural state, it's called the ground state. So here we can see an example of absorption spectra. So here if we have an electron that is moving up an energy level, we would have absorption. If it falls from the second orbital down to the previous one, that would give us an emission spectra. So as it moves up, it absorbs. As it falls down, it emits. And we can see this by using something called a spectroscope, and we'll be using this in a lab in the next week. And a spectroscope you can think of as being similar to a prism in that it splits light into each of its component parts, except a spectroscope has a diffraction grating in which you can actually see all of the different elements and the different colors and absorption bands. So here is an example of what you would actually see through a spectroscope. So we have a continuous spectra in which you just see a continuous rainbow. So this would be emitted from a hot object under high pressure. So an example would be a star. We'd also see emission lines, and emission lines and absorption lines are actually mirror opposites. So if you have an object that is absorbing specific wavelengths or specific elements, it is also going to be emitting those elements. So a star's absorption and emission spectra are going to be the same. So because if it's absorbing, you would have these black gaps where it would be emitting them. So the absorption and emission lines are going to directly correspond. So emission would be black with the colored lines, and this would be an example like a hot gas under low pressure, such as a nebula. And absorption lines would be a hot object viewed through cooler gas. And this is actually what we'd see when we look at a star like our sun, because the outer layers of the sun are actually cooler than the inner layers of the sun. So here we can see one of those examples again. We can see our heat source. The heat source itself would produce a continuous spectra. If we have a gas cloud, such as a nebula or outer layer of star, as it passes through, that gas is going to absorb specific wavelengths or specific elements, and the gas cloud itself would produce an emission spectra. This is called Kirchhoff's laws of radiation. He was the one that first discovered this back in the 1800s. So in looking at, for example, a light bulb that has a filament on the inside, if you were looking at that light bulb, just the bulb itself, you would be able to see a continuous spectra. And you could see this in looking at the lights in our classroom. Whereas if you were to look at something that was a lower density, that was excited, had atoms that were elevated to higher energy levels, that would be kicking off photons, that would then give us an emission spectra. And emission spectra are what we can specifically use to identify elements. So hydrogen would look like this. You would have a lot more in the blue and the purple region. Neon has a lot more in the red and the orange region. And stars contain all of these elements. In fact, stars are the source of all of these elements. If there were no exploding stars, we wouldn't have these elements on Earth at all. We wouldn't have any of the heavy elements in the Earth's crust. We wouldn't have any of the gases that are present in our atmosphere. Exploding stars are what give us all of those elements. And these are the spectra of each of those individual elements that are specific to them. And here is our absorption spectra. So if we were to see that hot gas coming through something that was cooler, we would then have absorption of some of those specific elements by that gas. So again, the gas itself would give us an emission, but the original hot source, as it passes through the gas would absorb some of the elements from the heat source, and that would give us an absorption spectra. So here, each of the gaps, each of the black lines are specific elements that were absorbed as they passed through that gas cloud. Here's an example of an absorption spectra of the sun. We can see it looks pretty complicated, and if you were to look individually at each of these lines, you could see they each correspond to different elements, and you can see there are some that are much bigger gaps, much more being absorbed. And you can see for the sun, we have a lot more in the blue portion of the spectra than we do up in the red. And that's because our sun is more primarily hydrogen. And the spectra of stars are generally all going to give us absorption spectra, and that's because of the outer layer of the sun, the photosphere, being cooler than the core on the inside. So the photosphere itself is acting to absorb some of that. So stellar spectra is actually how we classify different types of stars. So we can classify them based on their temperature, and we know that if stars have a similar spectra, that they are going to have similar characteristics. So we know that very, very hot type O stars are going to be predominantly more ionized helium. They're going to have weak hydrogen lines. They're going to radiate in the ultraviolet. And that would mean that they're generally greater than 30,000 degrees. So this would be like examples of the stars in Orion's belt. So this is the order of stellar spectra. I said earlier you might need to know this. O, B, A, F, G, K, M. And the acronym that you can use to remember this is O, be a fine girl, kiss me. And that will greatly help you to remember which stars are the hottest. Our type O is going to be our hottest star, our type M is our coolest star, and our sun is a type G star. So because our star radiates at about 6,000 to 5,000 degrees Kelvin, that means we have to see it as yellow. So we could see each of these different temperatures correspond to a different color. So we can see here the temperature range. Here we could see the peak wavelength in a particular color. So we can see that as the star cools down, they're more red or only visible in infrared. So class M stars many times are not even visible in the colored portion of the spectra at all. So here again, some examples of stellar spectra, their color, their temperature, and their absorption lines. And again, that acronym is O, be a fine girl or guy, whatever your preference, kiss me. So here is an example of hydrogen alpha lines. This is in an emission nebula. So remember, nebulas are areas of hot gas where you have star formation, and hydrogen alpha lines are what dominate those. So usually this spectra is recorded digitally, so we would see a graph, and we could see that where we have these gaps in these absorption lines, we could see that we have a trough in the spectra. So we can see that we have this big dip where there's nothing being absorbed. And we can see this as intensity versus wavelength. So that is it for this portion of your notes, guys. I will see you in class.